you again. This is the last lecture of week 10. Last time I had introduced you to testing of object-oriented applications. This was an outline of the talks that I had discussed with you. We will look at an overview of some of the features of object-oriented software. We've already done some in the context of mutation testing for object-oriented integration. And then we said we'll discuss about what are the kinds of faults or errors that will come in object-oriented software. We'll follow it up with testing of object-oriented software. Yo-yo graph is something that we already looked at in the last module. And then in the next lecture, I'll end it with object-oriented call coverage criteria. Today, what I'm going to focus on is what are the errors in object-oriented software. We've already done overviewing of object-oriented features. So I had introduced you to inheritance, polymorphic methods, and what is the class hierarchy, what could be the various anomalies with object-oriented testing. And we had ended last class by looking at this graph called yo-yo. Now, moving on, what I'm going to do today's lecture is focus on faults or errors that come specifically related to object-oriented programs, specifically with reference to the object-oriented features that we have seen till now. Now, what will be the complexity or the main source of errors? The main source of errors, as I told you, because we are focusing on which level of testing, if you go back to the slide that I had looked at, we are focusing here. We are focusing on intra-class and inter-class. So which means what? We are focusing on various components and how they are going to interact. So our complexity or focus will be on the connections amongst these components. The problem with object-oriented software, as we have seen till now, is that the amount of static determinism is very less, in the sense that suppose I make a method call another method, or let's say I make a function call another function in C, I know that this is how the call is going to happen. Nothing is going to be different, whereas that's not true for an object-oriented programming language. If a method calls another method, the method that is being called can be overridden. The method that is calling can be overridden. One of these methods could be polymorphic. All kinds of interactions can happen. Nothing is statically determined. A lot of things depend on dynamic execution. As I told you, the complicated features that we've recapped reasonably well, like inheritance, polymorphism, they yield vertical integration, dynamically changing integration. And there are aggregation and use relationships that also add to the complexity. And typically designers, when they design encapsulation and abstraction, they don't consider visibility of data and methods because they consider it as a tester's problem. So now what we are going to look at in this lecture is just completely understand some of the faults that come because of these features: inheritance, polymorphism, constructors, visibility, and so on. While we understand these faults, we'll make one assumption. We'll assume that the fault or anomaly is manifested through polymorphism in a context that uses an instance of an ancestor. That is, instances of descendant classes can be substituted for instances of an ancestor. Another thing that I would like to tell you is that the faults that I have described here are completely language independent. It's not like these are exclusive only to Java and they cannot be used for C++. They are generic faults that can arise in object-oriented languages that use these features. So they are independent of a particular programming language. So here is a table of the faults and anomalies that are commonly listed for method level, interclass and intra-class level testing of object-oriented applications. Don't worry too much about remembering these acronyms. They're just listed for convenience because it's useful to use them in slides subsequently, and while talking about it, you don't have to memorize them. So we will understand about the 9 kinds of faults or anomalies are listed here. I will explain about 5 of them in detail with examples illustrating what is the kind of fault or anomaly. The remaining 2-3 of them I'll just give an overview, and I'll point you to literature at the end of these slides where you could look up for additional information. So we'll look at inconsistent type use. State definition can be anomalous or inconsistent or incorrect. We look at indirect and inconsistent state definition. When it comes to constructors, there could be two different kinds of anomalous behaviors. I have decided to skip these two, ACB1 and ACB2, because we haven't really looked at constructors, class constructors in details. So I will skip these two, but I'll tell you in detail about the other things. We'll also do state visibility anomaly. So the first one in the list is inconsistent type use fault, ITU. So what is the cause of this fault? The cause of this fault is because a descendant class does not override any inherited method. So there is no polymorphic behavior, because nothing is overridden, everything is static. So you could think, what is the problem? So we'll understand it with an example. For example, consider a case where class C extends a particular class, say T, and C also adds new methods. An object sometimes is used as a C, sometimes is used as T, and sometimes is used as a C again. Now methods in T can put this object in a state that is inconsistent for C. That's why it's called inconsistent type use fault. What do we mean by a state? We mean by a state in any programming language, including object-oriented programming language, we mean the values of all the variables. So this last point, you must read it as methods can change the values of some of the variables, which results in object going into a different kind of state. So here is an example. Let's say we have these two classes. There's a class called vector, which uses a sequential data structure called array, and it supports direct access to all its elements. It has two methods. One method that does inserting an element at a particular point, and it also does removing an element at a particular point. There is a class stack. What does class stack do? It does the normal operations of a stack. It pushes or it pops an object. So to pop an object, it calls the method remove element from the inherited from the class vector. To push an object, it calls the method insert element inherited from the class vector. So here is an abstract piece of code. Again, like all the examples that we saw in the course, this code is not complete, but only a snippet of it is given, helping you to understand the core issue. So let's say there are three operations that happen in this code. Three push operations, string 1, string 2 and string 3 are pushed using this method in the class stack. And let's say at some point this method dump is called on S. Let's go and look at the code of dump. What does dump do? Dump removes an element at v of size -1, which means in this case it removes the middle element. So after a call to dump is made, when it returns, out of the three entities that were pushed into S, the stack S, only two of them are available. Now look at these series of calls of pops. First pop, out of the two elements that were available in S, the one that is available topmost gets popped out. Second pop, there's only one left, it gets popped out. Now for the third one, there is nothing to pop. The stack is already empty. Why is there nothing to pop even though there were three different pushes? That's because there was this call made to a method dump, which also used remove element, which the class stack did not know about. Because it used remove element, one of the elements went away. The class stack assumed that because there were as many pushes as that were pops, you would have elements for it to do 3 pops. But the elements were not there because this dump used. So this resulted in an inconsistent assumption on the state of S here. It assumes that there were 3 elements present, whereas actually only 2 elements were present. So this is a classical example of how inconsistent type use can occur. The next kind of fault that I want to explain is what is called state definition anomaly, SDA. What happens here? The state interactions of a descendant are not consistent with those of its ancestor. What do again we mean by state interactions? State interactions means operations that involve changing the state, which means operations that change one or more variables that are present in the state. So the refining methods fail to define some variables, and the required definitions that you need may not be available. We'll see an example that explains this in detail. Let's say there is a class X that extends W, and along with extension X also overrides some of the methods of W. The overriding methods in X fail to determine some variables that the overridden methods in W actually define. Here is an example. Let's say there are three classes W, X and Y. So W defines two variables U and V and has two methods M and N. X has one variable small x and has one method N, and Y has one variable W small w and has one method M. So this method M in W defines V, and this method N in W uses V. Let's say some piece of code. I have not given the actual piece of code. And let's say the method X in N also uses V, and let's say the method Y in M does not define V at all. So now for an object of actual type Y, there will be a data flow anomaly if a fault in M, if M is called and then N. Why? Because if M is called and then N, Ym does not define V. And Wm is the one that actually defines V. Ym does not define V, and Xn tries to use V. But there will be no V available for Xn to use. So this results in a variable not being defined, which means a part of the state not being defined, and hence it's called a state definition anomaly. The next kind of fault is state definition inconsistency fault, SDIH. Here what happens? A local variable is introduced into a class definition, and the name of the variable is the same as the name of the inherited variable. So there is some amount of inconsistency that can happen because two different variables share the same name. The inherited variable is hidden from the scope of the descendant. Of course, if you explicitly use this keyword super and refer to the variable V, then it's not hidden. But otherwise, you can assume that the inherited variable is hidden from the scope of the descendant. Now, a reference to V will actually refer to the descendant's V, because that's where it is rewritten. An anomaly can exist if a method that normally defines the inherited variable is overridden in a descendant when an inherited state variable is hidden by a local definition. So we'll see again an example. So consider the same kind of situation. We have three classes W, X and Y. W has two variables U and V, two methods M and N. X has a variable small x and a method N. Y has a variable small v and a method M. Now the catch is the variable Y, the class Y overrides this W's V. So which means what, these two V is the same, but this V overrides this V. Now the method M of Y defines this variable YV. Now X in this method N uses V, but whose version will it get? It will get W's version. Is that clear? So now for an actual type of object of actual type Y, there can be a data flow analysis if M is called and then N is called, because X is actually expecting W's version, whereas Y has already overridden it. So with the V that is sent is basically not the expected V. So the state part corresponding to that of V is inconsistent. So the next fault is state visibility anomaly. Consider a class W which is an ancestor of X and Y. X extends W, Y also extends X. Now let's say W declares a private variable V in a method M. Y overrides that method M, calls Wm to define V. Now this causes data flow anomaly because the call for Y is not well defined. Why? Because V is private for W, right? So which means the visibility or the access level of V is not consistent the way Y and W want to use it. That's what is wrong. So this is what is explained in the previous slide. Three classes W, X and Y. Y has a private variable V and defined by the method. W has a private variable V, defined by the method M. And Y has a method M that overrides this method. So Ym cannot call Wm because of the variable V is private to W. So that results in the visibility of V not being there. So that's what is called state visibility anomaly. There are several other faults that were listed in the table that I presented to you earlier. For a second, I'll go back to that table. So these were the faults. Why have I colored them these four green? Because I gave you examples for these four. That's why these 4 were colored green. I will also tell you what state defined inconsistently and indirect inconsistent state definition is. As I told you, we will not discuss the 3 constructor faults because I didn't introduce the notion of class constructor in detail to you. So I'll skip it in my lectures, but I'll give you references where you can learn more from it. So the 2 pending things without examples are state defined incorrectly and indirect inconsistent state definition. So we'll look at that. State defined incorrectly, what happens here? An overriding method defines the same state variable that the overridden method also defines. So obviously 2 variables defined by 2 different methods. One could say values 1, the other could say values the other. State will be defined incorrectly. In the absence of identical computations, if the 2 methods do identical computations, fine. But let's say 2 methods do different things, they could highly likely that they'll come up with different values for the same variable v. So the state gets defined incorrectly. The next is indirect inconsistent state definition fault. This is when happens when a descendant adds an extension method that defines an inherited state variable. The reference that I'll be pointing you to, you'll find examples for these also. Feel free to look at them and you can ping me in the forum if you don't understand anything or you have doubts. Moving on, what are we going to do in the next lecture? We'll look at how to test for these problematic features such that we detect the faults that we understood in this lecture. If you remember, when we did integration testing, data flow, using graphs and all that, we did data flow testing and we introduced the notion of coupling variable. We'll extend it to object-oriented coupling and we'll define data flow criteria over these coupling variables. So that's it for today. Thank you.